Now, if you look at these expressions, then you see that P eta, E and N, I can recast them as beta P eta is equal to minus eta g 2 eta g over square root pi 1 over lambda t integral 0 to infinity dx x to the power half ln 1 minus eta z e to the power minus x beta e eta is equal to twice eta g v over square root pi 1 over lambda t 0 to infinity dx x to the power 3 half z inverse e to the power x minus eta, and n eta is going to be twice eta g square root pi v 1 over lambda t 0 to infinity dx x to the power half divided by z inverse e to the power x minus eta, right? So I can simplify a little bit further, in the sense I can take the volume to the right hand side over here and over here and define the energy density epsilon eta as E eta over V and the number density n eta as capital N eta over V. So this means I have epsilon eta and I have n eta, right? But if you look at these expressions carefully, this describes the thermodynamics of an ideal quantum gas, but everything is in terms of the fugacity Z. And if I want to obtain the equation of state, I have to determine Z from this equation number density and replace this over here in this expression. For this, I define a function f eta of m as 1 over m minus 1 factorial integration 0 to infinity dx x to the power m minus 1 divided by z inverse e to the power x minus eta, right? In terms of f eta, beta p eta, the pressure, is 1. So in terms of this integral, the pressure becomes g over lambda t f 5 by 2 eta of x, and this follows from this expression that we have over here, this expression. N eta is going to be g over lambda t f of 3 half eta of x, and epsilon eta, which is the energy density, is going to be 3 half of p eta. So these are the expressions that we are going to work with. Now first, what I want to do is I want to look at the high temperature limit. The reason I want to look at the high temperature limit first is here I can take care of both the ideal fermionic gas and ideal bosonic gas using the same formalism. I don't have to do anything special. It's a low temperature which has to be treated separately, right? Now in the high temperature limit, which is also called the non-degenerate limit z is small, so that I have f eta of m as a function of z is equal to 1 by m minus 1 factorial integration 0 to infinity dx x to the power m minus 1 divided by, I can take z inverse e to the power x outside. This becomes eta z e to the power minus x, which is 1 over m minus 1 factorial 0 to infinity d of x x to the power m minus 1 this is z e to the power minus x divided by 1 minus eta z e to the power minus x, and this is 1 minus m minus 1 factorial 0 to infinity dx x to the power m minus 1 z e to the power minus x 1 minus eta z e to the power minus x raised to the power minus 1. So now I can do a binomial expansion of this term that gives me m minus 1 factorial 0 to infinity d of x x to the power m minus 1 z e to the power minus x sum over alpha eta z e to the power minus x raised to the power alpha, so that I have alpha is equal to 0 to infinity. M minus 1 factorial 0 to infinity dx x to the power m minus 1. I have eta to the power alpha sum over alpha is equal to 0. Okay, sorry, I cannot take it out. So that I have 1 over m minus 1 factorial 0 to infinity d of x x to the power m minus 1 z e to the power minus x sum over alpha is equal to 0 to infinity z e to the power minus x raised to the power alpha eta to the power alpha. I can bring it inside over here so that this becomes alpha plus 1, and then I can change the indices m minus 1 0 to infinity d of x x to the power m minus 1, so that I can write alpha plus 1 is equal to, let's say, alpha prime, so that alpha is alpha prime minus 1, and when alpha is equal to 0, alpha prime runs from so that I can change the indices by writing alpha. So that I can change the indices by writing alpha plus 1 is equal to alpha prime, so that alpha is equal to alpha prime minus 1 and therefore I have the new sum should run from 1 to infinity. I'm going to have alpha equal to 1 to infinity z e to the power minus x raised to the power alpha, and then I'm going to have eta to the power alpha minus 1. But I also note that eta square is plus 1. So I'm just going to multiply eta to the power alpha minus 1 with eta square, because eta square is 1, so it doesn't matter to me, and to get me alpha plus 1. There is a sum over alpha. So then I have 1 minus m minus 1 factorial sum over alpha equal to 1 to infinity. I have eta alpha plus 1. I have z to the power alpha, and then I have 0 to infinity dx x to the power m minus 1 e to the power minus alpha x. And this quantity is well known in the sense that I know how this thing is going to go. And this integral, I can replace x prime as alpha x, so that dx becomes x prime dx prime over alpha. And you see that this integral I can recast as 1 over alpha to the power m 0 to infinity dx x to the power m minus 1 e to the power minus x, which is nothing but the 1 minus m minus 1 factorial will cancel with this, and therefore you are going to be left out with alpha equal to 1 to infinity alpha plus 1 z to the power alpha divided by alpha to the power m. So which means the high temperature expansion, which we just worked out, for f5 half eta of z and f3 half eta of z is the following, or are the following. So f of 5 half eta of z means m is equal to 5 half is going to be, if I put alpha equal to 1, I have eta square z plus eta z square divided by alpha is 2 to the power 5 by 2 plus eta square z cube, I have 3 to the power 5 by 2 plus higher order terms. And I am going to have 3 half of z is equal to z plus eta z square 2 to the power 3 by 2 plus eta square z cube 3 to the power 3 by 2, so on and so forth. Since eta square is equal to 1, I can as well remove the eta square from here. We are going to use these two high temperature expansion of this function f. Now I know that n eta was g over lambda t f3 by 2 eta of z, and the idea is to determine z, the fugacity, from this equation. So if I write it down, then this becomes g over lambda t z plus eta z square 2 to the power 3 half plus z cube 3 to the power 3 half plus higher order terms, so that I have lambda t n eta over g is going to be z plus eta z square over 2 to the power 3 by 2 plus z cube 3 to the power 3 by 2 plus so on and so forth. Right? Now I want to determine z from this equation perturbatively. How to do the perturbative determination? So I can see that z is going to be lambda t n eta divided by g minus eta z square 2 to the power 3 by 2 minus z cube 3 to the power 3 by 2, and if you want to take the next term, it's going to be again eta z4 4 to the power 3 by 2 plus higher order terms. Good. So I immediately say that to the lowest order, my z1 is going to be lambda t n eta over g, plus the next order is going to be of order n eta square, because the next term is of the order of z square. So if you plug in this value, just this value of z over here, then you see that the next term is of the order of n eta square. What about z2? z2 is going to be n lambda t n eta over g minus eta. I'm going to substitute z1 into this expression. That gives me lambda t n eta over g whole square 2 to the power 3 by 2, and then I have order of n eta whole cube, which comes from this. I can determine z3 by substituting z2 in this expression, right? So and you are going to get the answer as lambda t n eta over g minus eta raised to the power 2 to the power 3 by 2 lambda t n eta over g whole square plus 1 by 4 minus 3 to the power 3 half n eta lambda t over g raised to the power whole cube plus order n eta raised to the power 4. So this is the perturbative way of evaluating the fugacity set. Now the idea is to use this and to look at beta p eta, which was g over lambda t f of 5 by 2 of z times eta. So let's see, this is going to be beta lambda t p eta over g is going to be f of 5 half eta over z, and this answer is z. If you go back to this approximation, it is going to be z plus eta z square 2 to the power 5 by 2 plus z cube 3 to the power 5 by 2 plus higher order terms. Now if I substitute z3 in the value of here in the expression for beta p eta, then I see that this is going to be lambda t eta, this is going to be lambda t n eta over g minus 2, so if I now substitute this value of z3 in this expression, I will come up with expression that this is going to be lambda t n eta over g minus eta 2 to the power 5 by 2 n eta lambda t over g whole square plus 1 by 8 minus 2 3 to the power 5 by 2 n eta lambda t over g whole cube plus higher order terms. So this is going to be beta lambda t p eta over g. So you immediately see that the lambda t over g cancels out from the left hand side, so that I have n eta, I can take this common as 1 minus eta 2 to the power 5 by 2. One factor of lambda t by g is going to cancel out from the left hand side, so I'm going to be left out with lambda t over g times n eta plus higher order terms. In fact, just to determine this correction, it is sufficient to keep up to the first order in Z1, so that the thermodynamic pressure of an ideal quantum gas using the canonical formalism comes out to be P eta as n eta kBt 1 minus eta lambda t 2 to the power 5 by 2 g n eta plus higher order terms, and you immediately see that this is the second virial coefficient. It's a correction over the ideal gas equation. P is equal to n kBt, and that correction B2 is minus eta lambda t over 2 to the power 5 by 2g. It's an identical correction that we obtained in the canonical ensemble when we did this in the using the canonical ensemble, except that there's an additional factor of g which we could have also taken care there, but we did not. Now we have done it explicitly in this case.